A tiny, dark world spins furiously in the frozen dark. This is Varuna, a dwarf planet hiding in the solar system's most distant attic, the Kuiper Belt. We are about to embark on a journey to its icy shores to uncover not one or two, but 25 of its most profound and unresolved secrets. By the end, you will possess a complete map of the enigmas that make this distant speck one of astronomy's greatest puzzles. How did it get an orbit that flings it wildly between the planets? And why does it spin so fast it should tear itself apart? The answers are stranger than fiction. What do you believe is waiting for us in that endless, silent dark? Its path through the solar system is our first great mystery. While most planets trace nearly perfect circles around the Sun, Varuna's orbit is a stretched oval, a cosmic ellipse of startling extremes. At its closest approach, it ventures within about 40 astronomical units of the Sun. One astronomical unit is the distance from the Earth to the Sun, a measure of 930 million miles. So 40 of those units is already an almost unimaginable remoteness, a place of perpetual twilight. But that is Varuna's neighborhood. Its journey then carries it outward, far beyond the familiar realm of the planets, to an astounding aphelion of over 100 astronomical units. That is 2.5 times farther out, a voyage into the deepest, coldest reaches of our solar system. Think of a world that experiences not seasons as we know them, but radical cosmic climate shifts. For part of its long year, which lasts nearly 300 Earth years, it receives a tiny fraction more solar warmth. For the far longer remainder, it is a lonely voyager in a dark so profound and a cold so absolute that the very air we breathe would freeze into solid blocks in an instant. This elliptical sprint creates a fundamental puzzle. How did a sizable world get flung onto such a wild track? The leading theory points to the gentle but persistent gravitational hand of Neptune. In the early solar system, as the giant planets shifted and settled into their current orbits, their immense gravity acted like a cosmic slingshot, hurling countless icy bodies into the distant Kuiper Belt or even ejecting them entirely into interstellar space. Varuna may have been one such object, receiving a precise gravitational kick from Neptune that set it on this elongated path without ever being captured as a moon. Yet, some astronomers wonder if Neptune's influence alone is sufficient to explain the specific stretch of this orbit. This leads to a more dramatic, albeit unproven, possibility. Could a gravitational nudge have come from something else entirely, a hidden world, a planet 9 or a rogue planetary body that once passed through the outer solar system? The extreme nature of Varuna's orbit makes it a key piece of evidence in the search for these unseen giants, a fossilized record of a violent, chaotic chapter in our solar system's youth. Because of this, modeling Varuna's precise history is notoriously difficult. Its path is a chaotic equation, sensitive to tiny perturbations over billions of years. Unlocking its origin story would not just tell us about Varuna, it would give us a clearer window into the gravitational storms that shape the very edge of our celestial home. This frantic orbital dance is mirrored by a violent internal spin. Varuna whirls around its own axis at a speed that defies easy understanding, completing a full rotation in just 6 hours and 20 minutes. For a world estimated to be over 400 miles across, this is a breathtakingly fast pirouette. To grasp the scale, picture our own Earth, which takes a leisurely 24 hours for one turn. If our planet spun that fast, centrifugal force would stretch the oceans toward the equator and pull the very ground apart. For a relatively small, icy body like Varuna, the physical consequences of this spin are not just dramatic, they are defining. The simple, relentless physics of rotation dictate that such a fast spin should have pulled and stretched the dwarf planet into a profoundly elongated shape, like a football or a lozenge tumbling end over end through the void. This expectation sets the stage for our second great mystery. What exactly does Varuna look like? We have no clear photograph of its surface, only subtle variations in the light it reflects as it spins. Those precious light curves, the fingerprint of its rotation, tell a story of extreme elongation, but the exact form remains hotly debated. One compelling model is the Jacobi ellipsoid. Imagine a lump of clay placed on a potter's wheel. As the wheel spins faster, the clay flattens at the poles and bulges at the equator, eventually stretching into a smooth triaxial ellipsoid, a shape like a flattened, stretched sphere. This is a stable form for a rapidly rotating fluid body, and if Varuna's interior is warm and malleable enough from radioactive decay or past impacts, it could have settled into this elegant, elongated form. Yet another possibility is far more chaotic. Varuna might not be a single, stretched world at all, but a contact binary. This is the cosmic equivalent of two snowballs pressed gently together until they stick. Two sizable icy bodies formed separately in the early solar system could have drifted together in a slow dance and merged in a gentle collision, creating a single, lumpy, peanut-shaped object. The rapid spin we see today could even be the leftover momentum from that ancient, graceful merger. Each model tells a different story about Varuna's history and interior. A Jacobi ellipsoid suggests a world that was once molten or soft enough to flow into an equilibrium shape, hinting at a warm, dynamic past. A contact binary speaks of a quieter accretion, a peaceful coming together that preserved the identities of two primordial building blocks. The truth sculpted in ice and rock out in the dark holds the answer to how such distant worlds are truly built. The very color of this distant world is a clue written in faint light. Varuna presents itself to our telescopes not as a bright, reflective snowball, but as a dim, reddish-tinted speck. This hue is far from random. It is the signature of a surface that has been cooked and processed by the harsh environment of deep space for billions of years. Spectral analysis, the technique of breaking its reflected sunlight into a rainbow of colors to find the chemical fingerprints of specific materials, confirms the presence of water ice. But the data also tells a more complex story. The ice is not pure and crystalline. It is darkened and altered, likely mixed with complex organic compounds known as tholins. These are not signs of life, but rather the opposite. They are the products of lifeless chemistry. When simple ices like methane or nitrogen are bombarded for eons by cosmic rays and ultraviolet radiation from the sun, even at that incredible distance, they break apart and recombine into these reddish, complex organic polymers. Think of it as a kind of cosmic suntan, a slow-burning chemical process that stains the surface a deep brick red over geological time. This leads us directly into the third great mystery. If Varuna is coated in these dark, complex organics, why does its surface appear to have less simple water ice than we might expect, especially when compared to a similar-sized neighbor like Kuiper? Kuiper shows stronger spectral signatures of crystalline water ice, suggesting a fresher, perhaps more recently active surface. Varuna, in contrast, seems older, more processed, and curiously dormant. One possibility is that Varuna's wild elliptical orbit plays a key role. As it swings closer to the Sun during perihelion, even that tiny increase in solar energy might be enough to trigger a brief, weak form of atmospheric activity. Frozen volatiles on the surface could sublimate, turning directly from solid to gas. And then, as Varuna journeys back into the deep freeze, that gas might refreeze not as bright, fresh ice, but as a darker, more amorphous frost mixed with the existing tholins, further masking the icy signature. Another, more dramatic theory involves internal heat. Perhaps in its distant past, Varuna experienced enough radioactive heating or was warmed by the energy of a giant impact to briefly create a subsurface ocean or slushy layer. This could have allowed darker material from its interior to rise and mingle with surface ices, or caused chemical reactions that created a global layer of dark sludge that then refroze. The surface we see today would then be a kind of ancient, stained crust, a relic of a more dynamic youth. The contrast with Kuiper suggests that not all Kuiper Belt objects share the same history, even if they formed in the same neighborhood. Varuna's reddish, processed face is a diary of its unique experiences, a record of relentless radiation, possible climatic swings, and internal secrets we are only beginning to read. What other compounds might be hiding in that red tint, and what do they whisper about the building blocks of planets in the coldest places imaginable? The puzzle of its color deepens when we try to measure its most basic property, how much light it actually reflects. This is the albedo, a world's brightness, and for Varuna it has been a shifting, elusive number. Early observations, based on its faint glow and estimated size, painted it as one of the darkest denizens of the Kuiper Belt, a charcoal black world reflecting only a tiny fraction of sunlight. This fit the picture of an ancient, radiation-cooked surface coated in dark tholins. But science thrives on better data, and more recent, precise measurements have complicated that simple story. The new data suggests Varuna's albedo is not uniformly dark. There appear to be patches, regions, where the surface is significantly brighter. This creates our fourth great mystery. What is causing these stark variations in brightness on a world so distant and cold it should be frozen in time? Several compelling possibilities emerge from the eternal ice. The first and most straightforward is impact gardening. Even in the sparse Kuiper Belt, collisions happen over billions of years. A fresh impact from a smaller object could blast away the dark, reddened upper layer, excavating and scattering brighter, cleaner water ice from beneath the surface. This would create a brilliant, reflective scar, a cosmic pothole filled with pristine snow. Over millennia, that bright spot would itself darken under the relentless radiation. But if impacts are frequent enough, Varuna's face could be a mottled tapestry of old, dark terrain and newer, brighter craters. A second, more dynamic possibility involves its wild elliptical orbit and the concept of seasonal sublimation. As Varuna swings slightly closer to the Sun during its perihelion, the minuscule increase in solar energy might be just enough to cause the most volatile ices on its surface, like frozen nitrogen or methane, to turn directly to gas. This process of sublimation could leave behind a lag deposit, a thin layer of slightly less volatile, brighter water ice grains, temporarily increasing the reflectivity of certain areas. Then, as it journeys back into the deep freeze, fresh frost could condense, creating a bright, thin coating. This would make Varuna's brightness a changing thing, a faint pulse tied to its 300-year seasonal cycle. The most speculative, and therefore most intriguing, idea is some form of residual geological activity. Could there be cryovolcanoes or ice volcanoes on Varuna? If its interior retains even a whisper of heat from its formation or from radioactive decay, it might be enough to occasionally force a slushy mixture of water, ammonia, and other ices up to the surface through cracks or vents. This would flood an area with bright, fresh cryolava that would then freeze solid, creating a brilliant, smooth plane against the darker background. While considered less likely for a world of Varuna's size, it is not impossible, and the presence of bright patches keeps this tantalizing door slightly ajar. This albedo enigma is not just an academic curiosity. It has direct, frustrating consequences for astronomers trying to understand Varuna's fundamental nature. We cannot fly a tape measure out to the Kuiper Belt, so a dwarf planet's size is calculated by combining two pieces of information: its thermal brightness, which tells us how big and warm it is, and its optical brightness, or albedo, which tells us how reflective its surface is. If you get the albedo wrong, you get the size wrong. A darker surface means the object must be larger to reflect the small amount of light we see. A brighter surface means it can be smaller and still appear just as bright. Because we do not know the exact mix of dark and bright patches on Varuna, its true diameter remains uncertain, floating within a range of dozens of miles. And without a precise size, we cannot calculate an accurate density. Density is the golden clue. It tells us if Varuna is a solid ball of rock and ice, or a porous rubble pile loosely held together by gravity. So a few bright patches on a dark world ripple outward, leaving us unsure of how big it truly is, what it is made of, and what secrets its core might hold. That uncertainty about its surface leads directly to a question about what lies just above it. Could Varuna, in the deepest freeze of our solar system, ever possess an atmosphere? The very idea seems to defy logic. At its average distance, sunlight is 1,000 times weaker than here on Earth, and temperatures hover near a bone-shattering -230 degrees Celsius, a cold so absolute that gases like nitrogen and methane freeze solid into ice as hard as rock. An atmosphere should be impossible, a fleeting dream instantly frozen to the ground. Yet, the universe loves exceptions, and Varuna's wild elliptical orbit creates a tantalizing loophole. During its closest approach to the Sun, its perihelion, it receives a tiny but significant boost in solar energy. This could be just enough to warm specific, highly volatile ices on its surface. Imagine a patch of frozen nitrogen, a substance that on Earth is a gas making up most of our air. At perihelion, the surface temperature on Varuna might climb, not to anything warm, but perhaps just past the critical point where solid nitrogen turns directly into a gas, a process called sublimation. For a brief window in its 300-year journey, a whisper-thin, transient atmosphere of nitrogen or methane could puff into existence, clinging to the dwarf planet like the faintest ghost of a breath on a mirror. This would not be a sky you could breathe or see. It would be a vacuum 1,000,000 times thinner than Earth's air, but it would be a monumental discovery. Detecting such an ephemeral shroud from over 4 billion miles away is a Herculean task. Astronomers look for the telltale signs when Varuna passes in front of a distant star, an event called an occultation. If an atmosphere is present, even an incredibly thin one, it will bend the starlight slightly, causing the star to wink out not instantly, but gradually over a fraction of a second. It is like trying to measure the thickness of a soap bubble by watching how it distorts a streetlight from a mile away. So far, no occultation event has provided clear, unambiguous evidence for an atmosphere around Varuna. The results are frustratingly inconclusive, which in itself is a kind of clue. The absence of a detectable atmosphere, especially at perihelion, would be profoundly revealing. It would suggest that Varuna has lost most of its primordial volatile ices over the eons, perhaps stripped away by impacts or never having them in great abundance to begin with. Its dark, processed surface might be the barren crust of a world that has already exhaled its last volatile breath. Conversely, if a future observation ever catches that faint, seasonal puff of gas, it would rewrite our understanding of this distant object. It would prove that Varuna is not a completely dead world, but one with a slow, faint metabolic cycle tied to its orbit. More importantly, it would imply that the dwarf planet has managed to retain these light, volatile materials for billions of years, which suggests a surprisingly cold and undisturbed interior, or perhaps a crust porous enough to trap gases below the surface. The presence of a temporary atmosphere would also act as a geological agent, however weak. Gentle winds could redistribute dark dust and bright frosts, potentially explaining some of those puzzling albedo variations. It would transform Varuna from a static ice sculpture into a world with a faint, rhythmic pulse, breathing in and out once every 3 centuries. The search for this missing atmosphere is a search for the soul of the world, a quest to determine if it is a frozen relic or a body with a lingering whisper of change. But the mysteries of this world are not confined to physics and chemistry alone. They extend into the very name we have given it. Varuna is not a random designation. It is a title steeped in ancient myth, chosen with deliberate purpose by its discoverers. In 2000, when astronomers Michael Brown and Chad Trujillo confirmed this distant speck as a new world, they looked to the pantheon of Hindu mythology for its name. They selected Varuna, one of the oldest and most significant deities in the Vedas, the ancient scriptures of India. This god was not a god of war or love, but the sovereign of the sky, the oceans, and the cosmic order itself, known as Rita. He was the all-seeing celestial judge, the one who upheld the laws of the universe, observing everything from his lofty domain. There is a profound, almost poetic resonance in this choice for a dwarf planet hiding in the outermost dark. Just as the deity Varuna was believed to see all that transpired under the sky, our scientific instruments now strain to see this tiny world, to uncover every secret it holds from its unimaginable distance. We are playing the role of cosmic observers, trying to pierce the veil of deep space to understand its laws. More strikingly, the god Varuna was bound by and served the unbreakable cosmic order, Rita. And what is science, if not our human attempt to understand that very same cosmic order, the fundamental laws of physics and chemistry that govern everything from the spin of a dwarf planet to the stretch of its orbit? Every mystery we have explored so far, the wild ellipse, the frantic rotation, the reddened surface, each one is a puzzle set by the universe's own laws. In seeking to solve them, we are engaging in a modern form of myth-making, trying to comprehend the rules that bind Varuna just as the ancient seers sought to comprehend the principles that bound their world. The name transforms this icy body from a mere day to point into a character in a much older story, a symbol of the eternal human quest to find order in the vast and often chaotic cosmos. It reminds us that our exploration is not just a collection of facts, but a continuous narrative, a dialogue between our curiosity and the universe's silent, enduring truths. What other secrets might this all-seeing namesake be keeping, locked in its frozen heart? The ancient name hints at cosmic order, but the modern data reveals a frustrating chaos of numbers. At the very heart of our understanding of Varuna lies a fundamental disagreement. We do not know exactly how big or how heavy it is. This is not a minor uncertainty. It is a profound discrepancy that shakes the foundation of every model we try to build. Different observation techniques, each rigorous in its own right, tell conflicting stories about this distant world's most basic properties. The first method relies on stellar occultations, those precious moments when Varuna passes directly in front of a distant star. By timing exactly how long the star winks out from multiple locations on Earth, astronomers can trace the precise silhouette of the dwarf planet against the stellar backdrop. These events suggest a larger, more elongated shape. Another method uses the power of space telescopes like Hubble and Spitzer to measure both the object's visible light and its infrared thermal emission. A warm object of a given size glows with a predictable amount of infrared heat. By measuring that heat and combining it with an estimate of surface reflectivity, scientists can back-calculate the size. These thermal measurements have often pointed toward a smaller, more compact Varuna. The results do not neatly overlap. They create a frustrating range where the true answer hides. Think of trying to determine the weight of a fruit by only looking at its shadow from different angles, while also feeling its faint warmth from 100 feet away. Each sense gives you a piece of the puzzle, but they do not quite fit together. The discrepancy may stem from Varuna's own complexity. Its extremely elongated shape means its silhouette during an occultation changes depending on its rotational phase, like trying to measure the width of a tumbling football from a single, fleeting snapshot. Furthermore, if its surface has a patchwork of dark and bright terrains with different temperatures, as the albedo mystery suggests, then the thermal emission becomes incredibly tricky to interpret. A dark patch absorbs more sunlight and gets warmer, emitting more infrared, making the whole object seem smaller than it is. A bright, cold patch does the opposite. We are trying to take the temperature of a world with an inconsistent cosmic fever. This size uncertainty cascades into a greater problem. We cannot calculate a reliable density. Density is mass divided by volume. If the volume, the size, is a moving target, then the density is a guess, and density is the golden key that unlocks the internal structure. A low density, say around 1 gram per cubic centimeter like water ice, would suggest Varuna is a porous rubble pile, a collection of icy fragments loosely held together by gravity with plenty of empty space inside. A higher density, closer to 2 grams per cubic centimeter, would point toward a more consolidated, differentiated world. Differentiation is the geological process where a planetary body, heated during its formation, separates into layers. Denser rocky material sinks to form a core, while lighter icy material rises to form a mantle and crust. Did Varuna ever get warm enough for this to happen? Its rapid spin complicates everything. If it is a differentiated object with a dense core, its elongated shape could be a fossil from a time when it was molten and fluid, stretched by its own rotation before freezing into its current form. If it is an undifferentiated rubble pile, its shape is simply the result of 2 smaller piles sticking together. The unresolved size and mass mean we are left with 2 completely different portraits of the same world. One is a sophisticated, layered mini-planet with a secret history of internal heat. The other is a primordial snowdrift, a sleepy aggregate of the solar system's original icy building blocks. Until we can pin down its true dimensions, Varuna's deepest secret, the nature of its heart, remains locked away. This unresolved portrait of its interior leaves one startling feature completely unaccounted for, a feature that would rewrite the rules for such a distant world. There is a chance, a slim but compelling one, that Varuna is not alone in its silent spin. It may be adorned with a ring system. The very idea seems to belong to gas giants like Saturn, not to a small, frozen dwarf planet in the Kuiper Belt's deep freeze. Yet, we now know rings are not exclusive to giants. In 2017, astronomers made a stunning discovery. As the oblong dwarf planet Haumea passed in front of a star, the starlight did not simply vanish and reappear. It flickered, dimming briefly both before and after the main occultation. This was the unmistakable signature of a narrow, dense ring of particles orbiting Haumea. Suddenly, rings became a plausible feature for other large Kuiper Belt objects. This discovery turned every subsequent stellar occultation into a potential treasure hunt. On one occasion, observations of Varuna itself showed a peculiar, unexpected dimming in the starlight just before the main event. It was not a clean, sharp cutoff, but a subtle, brief fade. Could this have been the shadow of a ring? The data was not as clear as Haumea's. It was a whisper, not a shout, leaving astronomers divided. Some believe it was merely noise in the data or an effect of Varuna's own extremely elongated shape. Others see it as a tantalizing clue, a hint that we might have glimpsed the edge of a cosmic jewelry box. If real, such rings pose an immediate and profound question. How could they possibly exist so far from the Sun? At that distance, the particles that make up rings should not behave like they do around Saturn. There, delicate ice crystals and dust can persist for ages. In the Kuiper Belt, the material is different, often darker and more porous. More critically, the dynamical environment is strange. The particles should be subject to constant perturbations, not just from Varuna's own lumpy gravity, but from the distant tug of Neptune and the Sun. Over millions of years, these tugs should either disperse the ring entirely or cause the particles to coalesce into a small moon. For a ring to survive, it must be either very young, recently created by a spectacular collision that shattered a moon, or it is being actively confined by something we cannot see. One fascinating possibility is the presence of a tiny shepherd moon, a small satellite perhaps only a mile or two across, orbiting just inside or outside the ring, could use its own gravity to herd the ring particles, keeping them in a narrow, defined band. Our telescopes have not spotted such a moon, but that does not mean it is not there, hiding in the glare or lost in the darkness. The existence of a ring would fundamentally alter our understanding of Varuna's environment. It would imply a recent, violent history, a cataclysm that provided the raw material. It would also create a dynamic, messy zone around the dwarf planet, where particles constantly collide and drift, potentially raining down onto the surface and creating those puzzling bright patches we see. A ring would transform Varuna from a solitary ice sculpture into the center of a miniature, intricate system, a hidden hub of activity in the stillness. The search for this phantom ring continues, a testament to the fact that even in the oldest, coldest reaches of our solar system, the potential for surprise is never zero. A ring would be a delicate crown, but so far we have found no jewels to place upon it. The search for moons around Varuna has been a persistent and surprisingly empty endeavor. While our telescopes have grown ever more powerful, scanning the deep dark around this spinning world, they have returned only silence and empty space. This moonless state is in itself a profound anomaly. Look across the Kuiper Belt at other sizable worlds, and you find a cosmos of companions. Pluto has 5 moons, including the giant Charon. Haumea has 2, Eris has 1. Even smaller, more distant objects like Orcus and Quaoar boast their own satellites. It is as if we walked into a grand party and found every other guest paired in conversation, while Varuna stands utterly alone in the corner. This isolation begs for an explanation, and the theories that emerge paint pictures of a violent or restrictive past. The first and most dramatic possibility is that Varuna once had moons and lost them in a cosmic catastrophe. A colossal impact early in the solar system's history could have been so violent that it not only shaped Varuna's rapid spin and elongated form, but utterly obliterated any orbiting satellites or flung them permanently into the dark. The debris from such an event might have briefly formed a ring which then, without a shepherd moon to contain it, simply dissipated over the eons, leaving nothing behind. The alternative is that Varuna's unique physical properties make it a poor host for moons. Its extremely rapid rotation and highly elongated shape create a chaotic and uneven gravitational field. For a potential moon, orbiting Varuna would not be like circling a smooth, round planet. It would be like trying to orbit a tumbling football, subjected to constantly shifting tugs and pulls. Stable orbits, especially close-in ones, might simply be impossible in such a turbulent environment. Any small body that ventured too close could be torn apart by tidal forces or hurled away by a gravitational kick at just the wrong moment. This could mean Varuna has always been solitary, its very nature forbidding the formation of a lasting companion. The absence of a moon is more than a curious fact, it is a major roadblock in our quest to understand this world. Finding even a tiny satellite would immediately solve one of our greatest mysteries, Varuna's mass. By observing the moon's orbit, its speed and distance, we could apply Newton's laws of motion with beautiful precision to calculate the exact mass of the dwarf planet it circles. With a known mass and a resolved size, we would finally, definitively, know Varuna's density. That single number would unlock the door to its interior, telling us instantly if it is a differentiated mini-planet or a porous rubble pile. A moon would be a key, a natural probe granted by the cosmos to weigh this distant enigma. Its continued absence forces us to rely on indirect, conflicting methods, leaving the true nature of Varuna's heart shrouded in ice and uncertainty. Is its solitude the mark of a traumatic past or the signature of a fundamentally unstable present? The empty space around it speaks volumes, but in a language we are still struggling to translate. The profound silence of its empty orbit points toward a history of violence. If Varuna truly has no moons, and if its frantic spin and elongated shape are not the product of a gentle merger, then the evidence points to a single, cataclysmic event in its deep past, a giant impact. This is not a mere scratch or a crater, but a collision of such staggering force that it could have reshaped the very soul of this world. We must now search its frozen surface for the scars of that ancient trauma. Given its likely rubble pile structure, a loose aggregation of ice and rock held together by gravity, such an impact would not have created a neat, bowl-shaped crater like those on our moon. Instead, the energy would have traveled through the entire fragile body, a seismic shockwave ringing through its porous interior. The result could be something far more dramatic, a global network of fractures, a spiderweb of cracks etched deep into the icy crust, or perhaps even a single, colossal impact basin so large it distorts the dwarf planet's entire form. When astronomers analyze the subtle light curves of Varuna, they are not just measuring its elongation, they are searching for these very signatures. A perfectly smooth ellipsoid would reflect light in a predictable, repeating pattern. But what if the pattern has tiny, consistent irregularities? A single massive basin, a depression hundreds of miles across, would create a permanent dimple in the light curve, a recurring dip in brightness as that scar rotates into view. Alternatively, a terrain shattered by fractures would scatter light differently than a smooth plane, potentially causing a more complex, jagged pattern in the data. The hints are tantalizing but frustratingly vague, hidden within the noise of measurements taken from across the solar system. A giant impact does more than leave a surface scar, it injects an enormous amount of energy. The heat from such a collision could have been enough to briefly melt Varuna's interior, allowing it to differentiate for a short time before refreezing into its current unknown state. This could explain a higher density without requiring long-lived internal radioactivity. More directly, the physics are irresistible. A colossal off-center strike is one of the most plausible mechanisms for setting a world spinning with the dizzying speed we observe. Imagine striking a loosely packed snowball with a glancing blow from a fast-moving rock. It would not just break apart, it would be sent tumbling end over end. That same principle, scaled up to planetary proportions, could have given Varuna its 6-hour day. And what of the missing moons? The debris ejected from such a violent meeting would have been tremendous, potentially forming a temporary disk of material that could coalesce into satellites. But if the impact was too violent, or if Varuna's chaotic gravity field was too unstable, those nascent moons could have been lost, either drifting away or falling back to crater the surface in a second reign of destruction. The scars of that ancient impact, if they exist, are therefore the master key. They could unlock the mysteries of the spin, explain the solitude, and hint at the internal structure. We are left staring at a faint, flickering point of light, trying to decipher if it holds the ghostly imprint of a hammer blow from the dawn of time, a wound frozen in place for billions of years. The ghost of a giant impact speaks of ancient fire, but what of warmth in the present? Could this frozen sentinel, so distant from the sun, still harbor a source of internal heat? The possibility seems to defy the very nature of the Kuiper Belt, a place where cold is the default state for eternity. Yet, for a world of Varuna's size, there are two potential furnaces hidden within its icy bulk. The first is the slow, steady decay of radioactive elements locked in its rocky core. Elements like uranium, thorium, and potassium, remnants from the supernova explosions that seeded our solar system, release heat as they break down over billions of years. For a small body, this heat usually leaks away into space too quickly to cause much action. But if Varuna is differentiated with a concentrated rocky core, that insulating blanket of ice above could act like a cosmic thermos, trapping the warmth and allowing it to build. The second, more intriguing source is tidal heating, but here the mystery deepens. Tidal heating requires a gravitational dance, a push and pull between two bodies, like the flexing that keeps the interior of Jupiter's moon Io molten. Varuna has no large moon to provide this constant kneading. However, its own rapid rotation presents a fascinating alternative. If Varuna is not a perfectly uniform sphere, but an elongated, lumpy rubble pile, its own rotation could cause its components to grind against each other. Imagine a bag of ice cubes tumbling endlessly in a cosmic dryer. The friction between those shifting blocks over eons could generate a subtle, pervasive warmth deep within. It would not be a roaring fire, but perhaps just enough to soften the ice, to create a slushy layer between a solid core and a rigid crust. This leads us to the most visually stunning possibility: cryovolcanism. On a world where temperatures are hundreds of degrees below zero, volcanoes do not spew molten rock. They erupt a chilly slurry of water, ammonia, and methane ices, a thick, antifreeze-laden mud that oozes onto the surface before freezing solid. If Varuna possesses even a whisper of internal heat, could such icy eruptions have stained its landscape? A cryovolcanic flow would be a geological event of stark contrast. It would coat the ancient, dark, reddened terrain with a bright, fresh layer of clean ice or complex organics brought up from below. This could perfectly explain the puzzling albedo patches, the bright regions that interrupt the otherwise dark face of the dwarf planet. These would not be impact scars, but frozen floods, ancient volcanic plains testifying to a time when Varuna's heart held a faint pulse. The composition of these hypothetical flows holds further clues. If the erupted material contained ammonia, it would act as a powerful antifreeze, keeping the slurry liquid at far lower temperatures and allowing it to travel greater distances before freezing. The detection of ammonia signatures on the surface, though incredibly difficult from Earth, would be a smoking gun for past cryovolcanic activity. Yet, the very factor that might generate internal heat, the rapid rotation, could also work against dramatic surface expressions. If Varuna's interior is warm and malleable, it may have simply flowed into its elongated equilibrium shape long ago, releasing its internal stresses smoothly rather than cracking its crust to create volcanic vents. The heat might be there but locked away, doing nothing more than gently softening the world's interior for billions of years, so we are left with a thermal riddle. Is Varuna a cold, dead relic, its internal fires extinguished eons ago? Or is it a world with a still warm core, its surface occasionally refreshed by the slow, frozen equivalent of a heartbeat, a testament to the fact that even in the deepest dark, the embers of creation can still glow? The search for internal heat leads us to a far more explosive possibility, one that connects Varuna to a cosmic crime scene. This is the controversial theory that it may be a member of the Haumea family. Haumea itself is one of the strangest worlds we know, a rapidly spinning, football-shaped dwarf planet with 2 moons and a faint ring. But its true claim to fame is its family, a collection of over a dozen smaller Kuiper Belt objects that share nearly identical orbits and, most tellingly, a unique surface composition rich in pure, crystalline water ice. The leading theory is that billions of years ago, a giant impact shattered a much larger, icy progenitor world. The largest remaining piece became Haumea, while the debris scattered across similar orbital paths, creating its icy kin. So where does Varuna fit into this picture? On the surface, the connection seems weak. Varuna's orbit is different, more elliptical and inclined than the tightly clustered Haumea family members. Its surface, as we've seen, is notably darker and redder, showing fewer strong signatures of that pristine water ice that defines the family. It seems like an outsider, a distant cousin at best. Yet some astronomers point to subtle, compelling clues. While not a perfect match, certain aspects of Varuna's reflectance spectrum do show hints of water ice, though it is heavily masked by dark organics. Could it be that Varuna is a fragment from that same ancient cataclysm, but one that was flung onto a different, wilder trajectory? Perhaps it was a core fragment or a piece that contained more rocky, dark material from the interior of the shattered parent body. After the impact, gravitational interactions, especially with Neptune, could have torqued its orbit into the extreme ellipse we see today, separating it from the main family cluster over eons. This idea would fundamentally rewrite Varuna's origin story. It would no longer be a solitary world that formed on its own. Instead, it would be a survivor, a shard of a forgotten giant, carrying the scars of that primordial violence in its very shape and spin. Its rapid rotation could be a direct inheritance from the spin of the progenitor or a result of the collision itself. Its elongated form might not be from a later, independent impact, but a frozen snapshot of the moment it was torn from a larger whole. The darkness of its surface could then be explained by its composition. If it were a piece of the parent body's darker, processed interior or crust that has simply undergone further radiation darkening over time. Proving this connection is incredibly difficult. It requires not just a similarity in composition, but a dynamical pathway that can be modeled to show how Varuna's current orbit could have evolved from the family's origin point. The orbital differences are significant, a gap that gravitational models struggle to bridge neatly. The debate remains open, a tantalizing what if that hangs over our understanding. If true, Varuna becomes a vital piece of evidence in reconstructing one of the largest collisions in the history of our outer solar system. If false, its isolation becomes even more pronounced, a world that stands apart in both its orbit and its lineage. Is it a lost sibling or a complete stranger? The answer is written in ice we cannot yet clearly see. The faint light we receive from Varuna carries more than just brightness, it holds a subtle, shifting hue. Recent, painstaking observations suggest this world's signature reddish tint is not a permanent stain, but may actually vary over its immense 300-year journey around the Sun. This is a revelation that transforms a static portrait into a living, breathing canvas. While the overall color remains within the spectrum of reds, the exact shade, the intensity of that ruddy glow, appears to pulse faintly in time with its orbit. It is as if the dwarf planet is slowly breathing, its complexion changing with the cosmic seasons. Unraveling this chromatic mystery requires us to look at the surface not as rock and ice, but as a complex chemical laboratory exposed to the elements of deep space. The primary artist here is likely relentless irradiation. For eons, cosmic rays and the faint but persistent ultraviolet light from the Sun have been bombarding Varuna's surface, a slow, invisible rain of high-energy particles. This radiation has the power to break apart the simple molecules in the surface ices, like frozen methane or nitrogen, and recombine them into those complex, reddish organic polymers called tholins. Think of it as a very slow, cosmic tanning process. If this were the only process at work, the color would simply get progressively redder and darker over billions of years, a one-way street to a deep burgundy. But the variation hints at other, cyclical forces at play. This is where Varuna's wild, elliptical orbit becomes a key player. During its closest approach to the Sun, the slight increase in solar energy might trigger a subtle but global phenomenon. The most volatile ices on the surface, perhaps a thin frost of methane or nitrogen, could sublimate, turning directly from solid to gas. This process would not be a violent geyser, but a silent, planet-wide sigh. As this gas lifts, it might carry away some of the darkest, finest dust particles that contribute to the red color, temporarily leaving a slightly less red, slightly brighter surface layer exposed. Then, as Varuna swings back into the deep freeze on the outer leg of its orbit, that same gas could recondense, falling back as a fresh, bright frost. This new frost would initially be less red, but would then begin its own slow journey toward a ruddy hue under the constant radiation barrage, only to be partially refreshed again on the next orbital pass. It is a slow-motion cycle of staining and cleansing, a chromatic heartbeat tied to the geometry of its path. There is another, more dramatic possibility. Varuna's surface may not be a uniform sheet but a dynamic shell. Micrometeorite impacts, though rare in the Kuiper Belt, are constant over geological time. A tiny impact, even from a grain of sand-sized particle traveling at tremendous speed, can blast away a small patch of the dark, reddened topsoil, revealing brighter, less processed ice beneath. If the rate of these small impacts is high enough, they could create a constant, faint churn on the surface, exposing fresh material that then slowly reddens, creating a delicate balance that shifts the average color over time. Each of these explanations paints a different picture of Varuna's present-day activity. If irradiation is the dominant, steady force, then the color variation must be driven by the competing process of frost deposition and removal, implying an active, if faint, volatile cycle. If impact gardening is the main driver, it suggests a surface that is constantly being subtly reworked, a testament to the slow but persistent bombardment that shapes even the most distant worlds. The very fact that we can detect this faint variation across billions of miles of space is a triumph of modern astronomy. It tells us that Varuna is not a museum piece frozen in a single moment, but a world with a rhythm, its face slowly changing under the influence of its star, its environment, and its own history. What other subtle cycles might be ticking away on that frozen surface, waiting for us to notice? The subtle rhythm of its changing color is only one clue hidden in its light. To truly listen to what Varuna is telling us, astronomers must become masters of its faint, rhythmic pulse, a science known as photometry. By measuring the precise brightness of that distant point of light over time, they can construct a light curve, a graph that rises and falls as the elongated world spins, presenting its broader and narrower faces to Earth. This light curve is the fingerprint of its shape and surface, and within Varuna's there is a peculiar anomaly. As the brightness climbs and falls in a predictable pattern, there is a small, consistent dip, a tiny gap or notch in the otherwise smooth curve. It is as if, during each 6-hour rotation, something briefly interrupts the flow of reflected sunlight. This is not the gentle slope of an elliptical shape. It is a specific, sharp feature etched into the data. A simple, smooth football tumbling through space would not create this. Something on the surface or just above it must be casting a shadow, either literally or figuratively, on the light we receive. The most straightforward explanation lies on Varuna's own frozen crust. This gap could be the signature of a major surface feature with a drastically different albedo. Imagine a single, enormous dark spot, a vast region stained even deeper red by complex tholins or covered in a blanket of primordial, charcoal dark dust. As this region rotates into our view, it absorbs more sunlight instead of reflecting it, causing the total brightness of the dwarf planet to momentarily falter, creating that distinct notch in the light curve. Alternatively, it could be a colossal impact basin. A deep, bowl-shaped crater hundreds of miles across would present a complex geometry of shadows and slopes. The interior walls of the crater might be in permanent shadow or angled away from the sun, creating a profound local dimming as it comes into sight. Such a feature would be a direct scar from the giant impact that may have shaped Varuna, a permanent monument to its most violent day. The consistency of the gap is key. It reappears at the same rotational phase every time, meaning this feature is fixed to the surface, a permanent landmark on this tumbling world. Yet, there is a more exotic and tantalizing possibility that exists just off the surface. The gap could be caused not by something on Varuna, but by something around it. This is the ghost of the ring theory returning. A narrow, dense ring of particles orbiting in Varuna's equatorial plane would, from our distant viewpoint, appear edge-on. As the dwarf planet rotates, this thin ring would periodically pass in front of the main body from our perspective, or its shadow would fall across the surface. The ring material itself, likely dark and dusty, would block a tiny fraction of the reflected light, or the structure could create a subtle shading effect. The gap's specific shape and depth in the light curve could, in theory, distinguish between a surface spot and a ring's transit, but with data so faint and precious, the interpretation remains hotly debated. Each possibility tells a radically different story. A dark spot speaks of ancient chemistry or a unique deposit. A crater screams of ancient violence. A ring whispers of a dynamic, recent cataclysm and a hidden miniature system. This tiny dip in a graph, a fluctuation almost lost in the noise, therefore becomes one of the most critical puzzles. It is a direct signal, a specific anomaly begging for an explanation that could, with one answer, resolve multiple other mysteries in a single, brilliant stroke of understanding. That subtle gap in its light curve is a whisper about its individuality, but to truly hear it we must listen to the chorus of other dwarf planets, placing Varuna alongside its more famous cousins, Pluto, Eris, Haumea, and Makemake, reveals it is not just another frozen world, but a distinct and extreme class of object. Pluto, for all its grandeur with 5 moons and a complex atmosphere, is a relatively sedate spinner, taking 6 Earth days to complete a single rotation. Eris, the most massive dwarf planet we know, rotates once every 25 hours. Varuna, by stark contrast, whips around in a mere 6 hours, making it the fastest spinning large body in the entire Kuiper Belt. This is not a minor difference, it is a fundamental divergence that speaks to a radically different history. Its orbit is another mark of distinction. While Pluto and the others follow paths that are moderately elliptical, Varuna's orbit is a stretched oval of startling proportions, carrying it on a far wilder journey between the inner and outer Kuiper Belt. This combination of extreme spin and extreme orbit sets it apart, a cosmic maverick even among the outliers. These differences point toward a potentially unique internal architecture. Pluto and Eris are believed to be differentiated worlds with rocky cores and icy mantles, their interiors possibly still warm enough to harbor subsurface oceans. Haumea's incredible spin and elongated shape suggest it is a differentiated body that was reshaped by a giant impact. Varuna, however, remains an enigma. Its unresolved density leaves us unsure if it is a consolidated, layered world like Pluto or a porous, undifferentiated rubble pile. Its rapid spin favors the rubble pile model, as a solid body might struggle to hold together under such centrifugal force without flowing into a new shape. This puts Varuna in a potential category of its own, a rapidly tumbling aggregate that never experienced the internal heating required to separate into core and mantle, a primordial snowball preserved in the deep freeze. What this teaches us is the breathtaking diversity of the Kuiper Belt. It is not a monotonous swarm of identical ice cubes. It is a dynamic menagerie of worlds shaped by unique collisions, gravitational encounters, and internal chemistry. Pluto is a complex planetary system in miniature. Haumea is a fast-spinning family patriarch surrounded by its children. Eris is a massive, almost planet shrouded in mystery. And Varuna is the wild-spinning, solitary voyager on an eccentric path, possibly representing the most primitive and unprocessed class of large Kuiper Belt object. Each one tells a different chapter in the story of the solar system's formation. Varuna's existence forces us to expand our definitions and our models, proving that even in the coldest, darkest attic of our celestial neighborhood, nature has crafted a stunning variety of frozen worlds, each with its own secrets waiting in the silent dark. The sheer scale of Varuna's orbit places it in a gravitational realm few worlds ever experience. At the farthest point of its immense journey, over 100 times the distance from Earth to the Sun, the dwarf planet enters a twilight zone where the Sun's grip grows astonishingly weak. Here, an even more profound force begins to exert its influence, the collective gravity of our entire galaxy. This is the realm of galactic tides, a mind-bending concept where the Milky Way itself can pull and push on solitary worlds. Imagine the Sun's gravity as a strong, familiar hand holding Varuna in a loose embrace. As the dwarf planet ventures to the outermost edge of that grasp, the gentle but immense pull of the galaxy's billions of stars becomes a competing force, a cosmic tide washing over it. These tides are not like ocean tides. They are a slow, relentless shearing force created by the difference in the galaxy's gravitational pull on the Sun and on Varuna itself. Over millions of years, this subtle tug of war can nudge an orbit, stretching it, twisting it, or shaking it loose entirely. For Varuna, this presents a profound and slow-motion mystery. Could these galactic tides be a hidden architect partially responsible for sculpting its extreme elliptical path? The gravitational kick from Neptune likely set it on its wild course billions of years ago, but the tides may have acted like a cosmic file, refining that orbit over eons. Each time Varuna swings out to its aphelion, that farthest, most vulnerable point, the galaxy gives it a microscopic gravitational nudge. Repeated over countless orbits, these nudges could have gradually pumped energy into its path, making the ellipse even more stretched than it was originally. It is a process of celestial erosion where the slow drip of galactic gravity carves away at orbital stability. This leads to a startling, long-term prophecy for Varuna. If these tides continue to perturb its path, they may one day provide the final, gentle push needed to eject it from the solar system altogether. In the distant future, billions of years from now, Varuna could become a rogue dwarf planet, untethered from the Sun, destined to wander the interstellar void alone. Its current wild orbit makes it a prime candidate for such a fate, a world already on the gravitational brink. This galactic influence adds a staggering new layer to Varuna's story. It is no longer just a resident of our solar system. It is a traveler on the very frontier where our Sun's domain gives way to the galaxy's vast sea. Studying its orbit with extreme precision becomes a way to measure the strength of these tides, to feel the fingerprint of the Milky Way on a single, tumbling piece of ice. It transforms Varuna from a distant curiosity into a cosmic gauge, a probe measuring forces that operate on scales almost too large to comprehend. The silence out there is not empty. It is filled with the faint, persistent pull of 100 billion stars, patiently shaping destinies in the dark. That galactic tide is a whisper from the present, but locked within Varuna's ice may be a shout from the very beginning. This distant world could be one of the most pristine time capsules in our entire solar system, a frozen relic preserving the original recipe of the protoplanetary disk. While planets like Earth and Mars were forged in fire and reshaped by geology and weather, the deep freeze of the Kuiper Belt acts as nature's ultimate deep freezer. At those unimaginable distances, chemical and geological processes slow to a near standstill. An icy grain that coalesced from the swirling cloud of gas and dust 4.5 billion years ago could, in theory, still be sitting on Varuna's surface today, unchanged and untouched. This is the profound promise of its remoteness. The chaotic, violent migrations of the giant planets that reshaped the inner solar system likely had far less influence in these outermost reaches. Varuna may have formed in place or very nearby and simply orbited in a deep, quiet sleep ever since, its composition a direct snapshot of the cold, primordial outer disk. Think of the protoplanetary disk as a vast cosmic mixing bowl. Closer to the young sun, where temperatures were high, only rocky and metallic materials could condense and stick together, leading to the terrestrial planets. Farther out beyond the frost line, it was cold enough for volatile compounds like water, methane, carbon monoxide, and ammonia to freeze into solid ice grains. These ices became the dominant building blocks for worlds like Varuna. On warmer, more active worlds, these original materials have been cooked, recycled, and transformed by internal heat and surface processes. But on a cold, dormant Kuiper Belt object, they may have simply been gathered together and left alone. Varuna's dark red color caused by tholins is not a mark of change but a mark of preservation. It is the result of that original, simple ice being slowly irradiated over billions of years, a process that records its age and isolation. The very fact that its composition seems different from neighbors like Quaoar suggests we are looking at distinct recipes from different parts of the ancient disk, each world a sample from a slightly different shelf in the primordial pantry. This makes Varuna a priority target for a future robotic mission, a journey that would be a pilgrimage to our own origins. A spacecraft, perhaps a dedicated orbiter and lander, could perform a kind of cosmic archaeology. It would not just map craters, it would taste the ice. By sampling the surface and subsurface material, we could analyze the precise ratios of different isotopes of hydrogen, carbon, and nitrogen locked in the ices. These isotopic fingerprints are like barcodes that tell us the temperature and conditions of the specific region of the protoplanetary disk where these molecules formed. We could measure the abundance of noble gases trapped in the ice, which hold clues about the early solar nebula's pressure and density. Most tantalizingly, we could directly study the complex organic tholins, not as signs of life, but as examples of the prebiotic chemistry that was happening everywhere in the young solar system, the raw ingredients that were later delivered to planets like Earth by comets and asteroids. A mission to Varuna would be like finding the original, unopened bag of flour from the day the bakery was built, allowing us to understand the exact ingredients that went into making the entire cosmic loaf. Its silent, frozen form may hold the clearest record we will ever find of what we, and everything in our solar system, are truly made of. The pristine time capsule we imagine might have been violently broken open long ago. Among the many theories for its frantic spin, one stands out for its sheer cosmic drama, the binary rival theory. This is not a gentle merger of two snowballs, but a story of celestial theft and sibling rivalry on a planetary scale. The idea proposes that Varuna was not born alone, but as part of a binary pair, a twin system of two similar-sized icy worlds orbiting a common center of gravity, peacefully circling the Sun together. Then catastrophe struck, a gravitational encounter, most likely with the migrating planet Neptune in the early solar system, ripped through their delicate dance. In this chaotic gravitational slingshot, one of the twins was likely captured, flung into a different orbit, or perhaps even ejected from the solar system entirely. The other, our Varuna, was left behind but not unscathed. The violent gravitational pull of the passing giant would have imparted a tremendous rotational kick to the surviving world, setting it spinning with the dizzying, 6-hour day we observe today. It is a cinematic origin story, a cosmic robbery that left a lone survivor tumbling in shock. The evidence for this theory is compelling in its elegance. It neatly solves two major puzzles at once, the origin of the extreme spin and the perplexing absence of moons. The spin is a direct product of the gravitational trauma. The lack of moons is explained because the system's original companion was not a small satellite, but an equal partner, now lost to the void. Furthermore, binary systems appear to be incredibly common in the cold outer reaches. We see them everywhere, from the Pluto-Charon system to countless smaller Kuiper Belt object pairs. Forming as a binary might have been the rule, not the exception, for worlds of Varuna's size. Our own solar system's giant planets are surrounded by families of moons that may be captured binaries, and the asteroid Ida has a small moon, dactyl, evidence of pairing even in the rockier inner belt. So the idea that Varuna began life with a twin is not far-fetched, it is almost expected. Yet the theory faces significant hurdles. The most glaring question is, where is the other one? If the twin was merely scattered onto a different orbit, it should still be out there somewhere, a world of similar size and composition, perhaps waiting to be discovered. Our surveys of the outer solar system, while incomplete, have not yet found a clear candidate that matches Varuna's expected sibling. If it was ejected entirely, that requires a very specific and powerful gravitational kick, which, while possible, adds a layer of complexity to the model. Additionally, the binary disruption theory must also account for Varuna's extreme orbital ellipse. The same Neptune encounter that tore the twins apart would also have dramatically altered the survivor's path around the Sun, which fits. But modeling such a precise event, one that imparts the exact right spin and the exact right orbital stretch, is a delicate astrophysical ballet. It requires a perfect cosmic billiard shot. Some scientists argue it is more likely that Varuna's spin and shape are the result of a direct, shattering impact, which could also explain potential surface scars rather than the clean gravitational theft of a companion. The binary rival theory is beautiful and haunting, a tale of loss written in spin. But until we find its missing twin drifting alone in the dark or rule out every other possibility, this remains one of the most captivating and unproven chapters in the story of our solitary, spinning sentinel. The silent ballet of a distant star holds the key to piercing Varuna's deepest veils. Stellar occultations are astronomy's most precise celestial measuring tapes, a fleeting moment when the dwarf planet glides perfectly in front of a far more distant star, casting a tiny, moving shadow upon the Earth. For a few precious seconds, that pinpoint of starlight winks out, and in that darkness lies a wealth of data. By timing the exact instant the star disappears and reappears from multiple observatories spread across the shadow's path, scientists can trace the precise outline of Varuna's silhouette against the cosmic backdrop. This is our only method for directly measuring its true shape and size without relying on assumptions about its brightness or temperature. It is a moment of truth, a chance to replace our models with a hard, cold silhouette etched in starlight. The results so far have been as surprising as they are crucial. Past occultations have strongly confirmed Varuna is no sphere. Its shadow is elongated, a stark validation of the extreme shape suggested by its light curves. But the data contained whispers of something more. The dimming of the star was not always perfectly crisp and instantaneous. There were hints of a slight, gradual fade at the edges of the event, a softness to the shadow's boundary. This subtle effect could have two explosive interpretations. First, it might be the signature of an extremely irregular surface, a world not shaped like a smooth football, but one with profound topographic features, deep concavities or towering ridges that graze the starlight. Second, and even more tantalizing, that soft edge could be the bending of starlight through a tenuous atmosphere. Even the faintest shroud of gas would act like a lens, causing the star to dim gradually rather than snapping off like a switch. Each interpretation leads to a different universe of understanding. An irregular profile points toward a rubble pile structure, a world so loosely held together that it cannot maintain a smooth equilibrium shape, its form dictated by the chaotic arrangement of its constituent blocks. A detectable atmosphere, however transient, would revolutionize our view of Varuna as an active, breathing world with a volatile cycle tied to its wild orbit. The frustration is that occultation events for an object this distant are incredibly rare and fiendishly difficult to predict and observe. The shadow path is narrow, often crossing remote oceans or inaccessible terrain. Yet, the astronomical community remains on constant watch, calculating orbits with ever greater precision. The next successful occultation is a potential gold rush of discovery. A perfect capture could, in one clean stroke, resolve the debates over its exact dimensions, confirm or rule out an atmosphere, and map the first true topographic features on its surface. It could tell us if we are looking at a shattered pile of rubble or a layered world with a hidden, gaseous whisper. Every mystery we have explored, from its density to its internal heat, waits for the definitive verdict that can only come when Varuna steps into the starlight and casts its shadow upon our world. The starlight that reveals its shape also carries the faint warmth of its surface, a warmth that tells a story of texture. This is the puzzle of thermal inertia, a fundamental property that measures how stubbornly a surface resists changing temperature. Think of walking barefoot on a summer day. Dark asphalt becomes scorching hot quickly under the sun, but cools rapidly when shade falls. It has low thermal inertia. A stone patio, however, takes longer to heat up and longer to cool down. It has high thermal inertia. For a distant world, we measure this by observing how its infrared glow, its heat signature, changes as it rotates from day into night. The data for Varuna points decisively toward a world with remarkably low thermal inertia. its surface temperature swings dramatically with the rhythm of its 6-hour day. This is not the behavior of solid bedrock or even consolidated ice. It is the signature of something fluffy, porous, and insulating. Picture a deep layer of fine, powdery snow, or a blanket of fragile, icy regolith, a dusting of material so delicate it has almost no ability to store or conduct heat. Sunlight does not penetrate it. It is absorbed in a thin, topmost layer, which then radiates that heat back into space the instant it rotates away from the sun. This finding has profound implications for what it is like to stand on that distant world. It suggests a surface that is incredibly pristine and undisturbed. Any substantial atmosphere, even a seasonal one, would create winds. Those winds, however faint, would slowly erode and smooth out that fluffy top layer, compacting it over time and increasing its thermal inertia. The fact that the surface remains so porous hints that atmospheric processes, if they exist at all, are vanishingly weak or incredibly brief. It is a landscape preserved in perfect stillness. This also means that any delicate features on Varuna could be preserved for eons. A fresh impact crater would not be weathered by wind or frost. Its sharp, jagged rim and ejected blanket of bright material would simply sit there, slowly darkening under radiation but otherwise unchanged. The potential giant impact basin, the dark spot, the cracks from ancient trauma, all these features would be sculpted not in hard rock, but in this cosmic powder snow, frozen in exquisite detail. This fluffy veneer might also act as a perfect insulator, trapping any remnant heat from the interior far below the surface, creating a stark thermal disconnect between the searing cold of the surface and whatever warmth might still flicker deep within. So the thermal inertia does not just describe a texture, it paints a portrait of a world in deep hibernation, its face covered by a blanket of primordial frost so delicate that to touch it would be to leave a mark that might last for millions of years. What delicate sculptures might lie undisturbed in that eternal powder, waiting in the silent cold? This delicate, powdery surface is a landscape we must one day visit. Among all the frozen worlds in the Kuiper Belt, Varuna stands out as a uniquely compelling target for a future robotic mission, a voyage that would be the ultimate deep space expedition. The challenges are monumental, dwarfing even the epic journey of New Horizons to Pluto. New Horizons took 9.5 years to reach its flyby. A mission to Varuna, which is often twice as far from the Sun as Pluto, would require a travel time measured in decades. We are talking about a spacecraft that might launch today and not reach its destination until the 2050s or 60s, a multi-generational project demanding extraordinary patience and long-term planning. The vast distance also means sunlight is vanishingly faint, requiring massive solar panels or, more likely, a nuclear power source like a radioisotope thermoelectric generator to provide enough electricity. Communicating with a probe that far away would be a whisper across a canyon, with data trickling back at painfully slow rates, a single high-resolution image taking days to transmit. Yet the scientific payoff would be nothing short of revolutionary, answering nearly every mystery we have pondered in one fell swoop. A dedicated orbiter could finally give us a clear portrait. We would see its true shape resolving once and for all, whether it is a smooth ellipsoid, a lumpy contact binary, or a shattered rubble pile. High-resolution cameras would map every dark spot and bright patch, identifying cryovolcanic plains or giant impact basins directly. A suite of instruments could search for that elusive ring system and any shepherd moons with certainty, scanning the space around it for the companions we have never seen. Most importantly, a mission could carry a lander or an impactor designed to sample that fluffy regolith. By analyzing the chemical and isotopic composition of its ices and tholins on site, we would be tasting the primordial solar nebula itself, reading the recipe of the outer solar system directly from the source. Compared to New Horizons' brilliant but brief flyby, A Varuna mission would ideally be an orbiter, a patient observer that could study the dwarf planet for years, watching for any seasonal changes as it moves along its immense orbit. It would transform Varuna from a flickering point of light into a world, a place with geography, history, and secrets laid bare. The journey would be the longest and hardest we have ever attempted, but the prize is a frozen chapter of our own origin story waiting in the dark to be read. The delicate powder of its surface is a testament to stillness, but its path through the solar system is a story of gravitational music. To understand the rhythm of Varuna's wild orbit, we must listen for a cosmic harmony known as orbital resonance. This is a delicate gravitational dance where two orbiting bodies exert a regular, periodic influence on each other because their orbital periods line up in a simple integer ratio. The most famous example is Pluto, which is locked in a 2 to 3 mean motion resonance with Neptune. For every 3 orbits Neptune completes around the Sun, Pluto makes exactly 2. This timing is not a coincidence, it is a protective lockstep. Each time Pluto catches up to Neptune's orbital neighborhood, their positions are arranged so that Neptune's gravity gives Pluto a consistent, gentle pull that reinforces its path rather than disrupting it. This resonance is the reason Pluto, despite crossing Neptune's orbit, will never collide with the giant planet. It is a gravitational safeguard written into the fabric of their motion. So where does Varuna fit into this symphony? The search for a similar protective resonance is our next great mystery. Neptune's orbital period is about 165 Earth years. Varuna's is approximately 283 years. The ratio of these two numbers is not a clean, simple fraction like 2 to 3 or 3 to 5. It is a messy, decimal relationship. This strongly suggests Varuna is not currently locked in a neat mean motion resonance with Neptune like Pluto is. It is marching to the beat of its own, far more chaotic drum. This absence of a stabilizing resonance has monumental implications for Varuna's past and its future. Without that gravitational anchor, its orbit is far more vulnerable to perturbation over astronomical timescales. The gentle but persistent tugs from Neptune and even the distant pull of the other giant planets can accumulate over millions of years, gradually pumping energy into its path. This could be a primary engine driving the extreme eccentricity of its ellipse, that stretched oval we see today. Each close encounter, even a distant one, acts like a tiny push on a child's swing. Without a resonant rhythm to synchronize and control those pushes, they can come at random times, sometimes adding energy, sometimes subtracting it, leading to an unpredictable and potentially unstable trajectory. This puts Varuna in a far more precarious long-term position than Pluto. While Pluto's resonance essentially guarantees its orbital stability for billions of years, Varuna's path is inherently chaotic. Computer simulations of its orbital evolution show it can behave unpredictably over long periods, its ellipse potentially growing even more stretched or its inclination tilting further. This lack of a resonant lock makes it a prime candidate for eventual ejection from the solar system, a future rogue dwarf planet, as those galactic tides and planetary nudges finally provide the push to set it free. Yet the story may not be so simple. Some dynamicists propose that Varuna could be in a much weaker, higher-order resonance, or that it might have been captured into a temporary resonance in the past that was later disrupted. The early solar system was a violent ballet of migrating planets, and a young Varuna might have been briefly captured into a resonant orbit that protected it during that chaotic era, only to be knocked loose by a later encounter with another large object. Its current wild orbit could then be the fossilized record of that lost resonance, a path frozen in time after its gravitational safeguard failed. Determining its precise resonant state or lack thereof is not just an academic exercise. It tells us whether Varuna is a permanent resident of our solar system or a long-term visitor merely passing through. It reveals whether its extreme path is a stable feature or a transient phase in a slow-motion catastrophe. The silence of a simple ratio speaks louder than any harmony, painting a portrait of a world forever dancing on the edge of gravitational chaos. The passage of centuries on Varuna is marked by a single, slow breath. While our planet cycles through spring and fall in mere months, this distant world experiences seasons that stretch across human lifetimes, each one a geological epoch in itself. Its 283-year orbit creates a climate of almost unimaginable patience, where summer and winter are measured in decades of continuous twilight or profound, star-filled night. The driver of this slow-motion climate is the feeble sunlight, which varies in intensity by a factor of 6 between its closest and farthest points from the sun. At perihelion, the sun appears as a painfully bright star, still over 1,000 times fainter than in our sky, but delivering just enough energy to cross critical thermal thresholds. At aphelion, it shrinks to a mere pinpoint, a distant campfire around which the frozen world huddles in near-total darkness for over a century. This staggering variation does not cause rivers to flow or storms to rage, but it may orchestrate subtle, planet-wide changes that redefine the surface over millennia. Think of a world where the very ground beneath your feet might sigh once every 3 centuries. As Varuna approaches its version of summer, that slight warming could be enough to vaporize the most volatile ices on its surface, particularly nitrogen and methane. This would not be an explosive geyser, but a planet-wide sublimation, a silent lifting of a molecular frost so thin it would be invisible to the human eye. For decades, this tenuous seasonal atmosphere might cling to the dwarf planet, a transient shroud only a few molecules thick. Gentle pressure gradients, the faintest whisper of wind, could then redistribute dark dust and bright frosts across the landscape, painting and repainting its albedo patterns over generations. Then, as the long fall deepens into an endless winter, this gaseous envelope would slowly freeze back onto the surface, falling as a new layer of ultra-cold snow, perhaps in different regions than where it left. The entire surface could be engaged in a slow, relentless migration of frost, a centuries-long game of musical chairs for volatile molecules. The thermal stress of this cycle may run even deeper. As the subsurface temperature changes across these epic seasons, the frozen crust itself may expand and contract. On a world that is likely a fragile rubble pile, this thermal flexing could generate minuscule seismic tremors, a gentle creaking and settling of the entire global structure. Over thousands of orbital cycles, this rhythmic thermal stress could be a key mechanism for gradually reshaping the terrain, smoothing some features and cracking others, all in silence and extreme slow motion. We are left with a profound modeling challenge. Our understanding of planetary geology is built on worlds with rapid cycles, where cause and effect can be observed within a human lifespan. Varuna's climate operates on a timescale we cannot directly witness. Our spacecraft missions are fleeting snapshots, capturing the world in a single seasonal moment, like visiting Earth on a random afternoon in July and trying to deduce the existence of winter. To understand its true nature, we must rely on complex computer simulations that play out these millennia-long processes, searching for the subtle signatures we might one day detect. The mystery is whether its face is eternally still, or if it is merely changing with a rhythm so slow and deep we have yet to learn how to listen. The long, slow sigh of its seasons is written into the very fabric of its being, a physical reality that brings us to the central, unifying question of this entire journey. After exploring 23 separate mysteries, from its wild orbit to its color changes, from its missing moons to its possible rings, they all converge on a single, unresolved enigma. What is Varuna actually made of? The answer lies in a single, elusive number, its density. This is not just another measurement, it is the master key, the final clue that will tell us if this tumbling world is a fragile snowdrift or a solid mini-planet. Yet this key remains frustratingly out of reach because to calculate density, you need two things, a precise mass and a precise volume, and for Varuna, both are maddeningly uncertain. The conflicting data from stellar occultations and thermal telescopes gives us not one size but a range. Is it a larger, more elongated 650 kilometers across or a more compact 550? This uncertainty of 100 kilometers, a gap wider than many countries, creates a cascade of doubt. The mass is even trickier without a moon to measure. Our best estimates are educated guesses based on comparisons with similar objects, leaving a wide margin of error. When we combine these shaky figures, the resulting density estimate is less a pinpoint and more a broad spectrum, a band of possibility stretching from a remarkably low 0.8 grams per cubic centimeter to a more substantial 2 grams per cubic centimeter. To understand what this range means, let us hold two very different worlds in our hands. At the lowest end of the scale, around 0.8, Varuna would be less dense than water ice. This is only possible if it is not a solid chunk, but a cosmic rubble pile, a loose aggregation of icy and rocky fragments with vast, empty pore spaces between them, like a freshly fallen snowbank in space. Its rapid 6-hour spin will be perfectly at home here, as such a fragile structure could easily be stretched into its elongated shape without breaking apart. The low thermal inertia of its fluffy surface would be the direct result of this porous interior. In this model, Varuna is a primordial relic, a collection of the solar system's original building blocks that gently came together and were then frozen in time, never experiencing enough heat to melt and consolidate. At the higher end, approaching 2 grams per cubic centimeter, the story changes completely. That density points toward a significant amount of rock mixed in with the ice, and more importantly, it suggests differentiation. This is the geological process where a planetary body, heated from within by radioactive decay or the energy of its formation, becomes a layered world. The heavy rocky material sinks to form a dense core, while the lighter ices rise to form a mantle and crust. A differentiated Varuna would be a sophisticated mini-planet with a secret history of internal warmth. Its rapid spin then becomes a monumental puzzle. How could a solid, layered body withstand spinning so fast without flying apart? The answer may lie in its shape. If it were once warm and malleable, it could have flowed under the centrifugal force, stretching into its elongated equilibrium form, a Jacobi ellipsoid, and then frozen solid. Its current shape would be a fossil of that hot, fluid past. Between these two extremes lies a universe of hybrid possibilities. Perhaps Varuna is a partially differentiated rubble pile, with a denser, compacted core surrounded by a looser, icy mantle. Its frantic rotation could be actively shaping its interior right now, the centrifugal force compacting material at its core while leaving the outer layers fluffy. Or consider the aftermath of a giant impact. A catastrophic collision could have shattered a once differentiated body, leaving behind a dense core fragment surrounded by a reaccreted shell of porous debris, a world with a solid heart inside a fragile body. This density dilemma is the grand synthesis of all our mysteries. The search for an atmosphere, the nature of the bright patches, the potential for cryovolcanism, the ghost of a ring, the absence of moons, every single clue is filtered through our assumption about what lies inside. A porous rubble pile cannot support a substantial atmosphere or dramatic geology. A differentiated body could have retained internal heat, potentially powering cryovolcanoes and creating those surface variations. Until we solve for that one critical number, Varuna remains two different worlds in our imagination, each equally plausible, each telling a fundamentally different story about the formation of the outer solar system. The silence from the Kuiper Belt is not an absence of information. It is a single, unanswered question echoing across 4 billion miles of space. What is the heart of this world made of? So where does this leave our lonely, spinning Voyager? Is Varuna the rule or the magnificent exception? This final mystery asks us to step back from the data and see the bigger picture. After 24 enigmas, we must decide if this world represents the standard model of a large Kuiper Belt object. Its puzzles merely symptoms of how little we truly know about that distant realm, or if it is a cosmic maverick, a one-of-a-kind world forged by a sequence of impossibly rare events. The evidence pulls us in both directions, forcing us to question the very categories we use to make sense of the solar system. On one hand, Varuna might be utterly typical. Its size places it among hundreds, perhaps thousands of similar worlds in the cold dark. We have studied only a handful up close. Its rapid spin, while extreme to us, might be common for objects of its composition and history. Its reddish color is the expected result of billions of years of radiation, a standard finish for ancient ice. From this perspective, every mystery we have catalogued is not a mark of Varuna's strangeness, but a glaring spotlight on the limits of our observation. We are trying to understand a complex, three-dimensional world from a single, flickering pixel of light. All large Kuiper Belt objects likely have unique impact histories, varied compositions, and complex shapes. Varuna's secrets may be the universal secrets of its class, simply waiting to be discovered on countless other distant orbs. Our struggle to pin down its density or confirm its atmosphere is not a story about Varuna. It is the story of remote astronomy itself, a humbling reminder of how much we still have to learn from the faint whispers of the deep. Yet the argument for its uniqueness is powerfully compelling. Look at the numbers. No other known object of its size spins that fast. Its orbit is among the most extreme of any large body we have catalogued. The apparent absence of any moon sets it apart from nearly all its peers. This specific combination of traits, a trifecta of extreme spin, wild orbit, and profound solitude, seems to point toward a singular biography. Perhaps it is the lone survivor of a shattered binary system, a story not shared by Pluto or Haumea. Maybe it endured a grazing, shape-altering impact of a very specific angle and force, a random cosmic bullet that missed its neighbors. Its path could be the rare result of a perfect gravitational kick from Neptune followed by billions of years of chaotic evolution, a dynamical path most other objects avoided. In this view, Varuna is not a standard model. It is a statistical fluke, a masterpiece of celestial chaos that happened to survive to tell its tale. It is the solar system's eccentric artist, living on the fringe and obeying only the rules of its own extraordinary past. This debate is more than academic. It strikes at the heart of how we explore. If Varuna is typical, then a mission to it becomes a mission to understand an entire population, a keystone that unlocks the story of the Kuiper Belt. If it is a true outlier, then visiting it becomes a journey to study a singular wonder, a cosmic unicorn whose value lies in its glorious deviation from the norm. Our categories of dwarf planet, Kuiper Belt object, and rubble pile strain under its weight. It defies easy labeling, refusing to fit neatly into any box we construct. And perhaps that is the ultimate lesson of this distant world. The universe does not create categories, we do. Out in the endless, quiet dark, reality is a spectrum of infinite variation. Varuna, in all its unresolved mystery, stands as a luminous challenge to our desire for simple order, a frozen reminder that the greatest discoveries often lie not in confirming what we expect, but in embracing the beautiful, confounding outliers that force us to see everything anew. 25 deep mysteries orbit this frozen world, a crown jewel of cosmic enigmas in the silent dark. From the wild ellipse of its path to the frantic 6-hour spin that should tear it apart. From its dark red, stained complexion to the puzzling bright patches that interrupt it, we have no clear picture of its face, no certainty of its size, no agreement on its weight. The question of a tenuous seasonal atmosphere hangs in the balance while the search for any moon has returned only empty space. Could it be a porous rubble pile or a differentiated mini-planet with a layered past? The ghost of a ring system teases the data, and the scars of a giant impact may be etched upon its surface. Does internal heat still whisper within, hinting at cryovolcanoes on a world of absolute cold? Its connection to the shattered family of Haumea is debated, while the slow pulse of its changing color tells of cosmic seasons. A peculiar gap in its light curve hints at a vast dark spot or a hidden ring, and its place among other dwarf planets highlights its extreme and solitary nature. Galactic tides sculpt its distant orbit, and its pristine ices may hold the raw recipe of the solar system. The binary rival theory tells a tale of a lost twin, while stellar occultations promise fleeting moments of truth. Its surface is a fluffy, insulating powder, a landscape preserved in perfect stillness, making it a prime yet daunting target for a mission that would take decades. It dances to no resonant rhythm with Neptune, leaving its future chaotic, and its epic seasons unfold over centuries-long breaths. All of these threads weave together into the final, unifying riddle, the master key we cannot yet forge, its true density and fundamental composition. Each unanswered question, from the grand to the granular, reveals the same humbling truth. The frozen frontier of our solar system is not a simple, silent vault. It is a dynamic, diverse, and deeply mysterious realm, and Varuna stands as its brilliant, spinning sentinel, reminding us with every flicker of its distant light how much we have yet to learn. So we turn the question to you. Which of these 25 mysteries captures your imagination the most? Is it the violent spin, the missing moon, the potential for a hidden ring, or the secret of its primordial heart? Let us know in the comments below, and if you are captivated by the enigmas of deep space, be sure to subscribe for more journeys into the unknown. Until next time, keep looking up.